Hey everyone, hope all of you are doing well. So in this video we'll be talking about Kirchhoff's current law in the light of some different examples, how it can be assessed, how this may be assessed in some exam type questions. So Kirchhoff's current law, and in some books it may also be called Kirchhoff's first law. If we are to recall what this statement really means, so there are a couple of ways in which it may be worded, and all of these are deemed correct by the examiner. So some of you might say that sum of currents entering a junction right, so all the current which is entering at a certain point equals the sum of currents which are also going to be eventually leaving the junction. Some books might also say that the algebraic sum of all the current entering a junction is 0, and again that actually means the same thing as what we wrote here. So now let's have a look at some of the examples. So this is the first one of those. So this question says a battery which has an EMF of 6 volts and negligible internal resistance. So later we'll also be doing questions related to internal resistance. Right now we can ignore this. Is connected to a 6 volt 6 watt light bulb in parallel. So we have the potential difference across this bulb, and we also know the power associated with this bulb. In parallel with another bulb which is also the same potential difference, 6 volts, but it has 4 times as much power as shown in figure 6. Right, so these are connected in parallel. Also sometimes the examiner may ask you what is the advantage of connecting lamps in parallel. So the idea is that each of these will have the same potential difference across them, right, and they will shine brighter. Right, so the brightness is greater when they are in parallel. And additionally, you may also know that if one blows out, then the other one will still be lit up, right? So the question says calculate in part A the current in each light bulb. So in each light bulb, how can we calculate the current? So we know that again, because both of these are in parallel, the current across the voltage, the potential difference across this is also going to be 6, is also going to be equal to the EMF of the battery, which is 6. So then if we know the voltage and we also know the power, then we can calculate the current which would be flowing in each of those branches. So if we use P equals VI, so for the bulb which is in this branch, the current would be 6 watts divided by 6 volts, so that would be 1 amperes. And then similarly if we do the same thing for the other one, so let's call this one I1, and then if we talk about the second branch, so if we say that this current is I2 flowing in the second branch, so that would be the power divided by the voltage again, but now this would be 24 upon 6. So this would be 4 amperes, right? So this is part A. In part B, the question asks us to calculate the current in the battery. So we can see from this diagram as well that this is like a junction, not like a, this is basically a junction, because the current being provided by the battery at this point would branch out into each of these parts, right? So this initial current branches out into I1 and I2. So what would that current entering be? So I can see that if this current is I, then it's very obvious that this is the current entering, so that must be equal to the current leaving. Just to make this even more clear, this is the current leaving at this junction. So I can say that by Kirchhoff's first law, the current entering is I, current leaving is I1 as well as I2. So sum of currents leaving is equal to sum of currents entering. So I1 is 1, I2 is 4, makes it a total of 5 amperes as the current which is provided by the battery. So this is the current flowing in this part, right? Even at these ends, this 1 and 4 would add up again to give you a current of 5 amperes in this part. Part C says the current, the power supplied by the battery. So that would be P equals VI, right? So the power is 6 and the current is 5. Sorry, the voltage is 6, the current is 5 through this battery. So this power would be 30 watts. And if you think about it, it makes perfect sense that out of the 30 watts which are supplied by the battery, 6 go to this lamp and 24 go to this lamp. Let's have a look at another question. So this question says a 2 ohm resistor and a 4 ohm resistor are connected in series, and then the series combination is connected in parallel with a 9 ohm resistor and a 3 volts battery of negligible internal resistance as shown. Calculate in part A the total resistance of the circuit. So because by definition resistance is the hindrance to the flow of current, always remember that always try to visualize the path of the current. So if this is the positive terminal, this is the negative terminal, this is how the current would be flowing, and then it branches out like this, and then it joins back up again at this point and then flows again into the battery. So it branched out here, and we can also see from the circuit that both of these would have the 3 volt appearing across it. The question also was very explicit in telling us how these are connected. So the 2 and 4 are connected in series, which is in parallel with the 9. So in part A, if we need to find the total resistance, if we call it RT, so that's going to be the 2 and 4 combination, which is going to be in parallel with the 9. So this can be represented as one resistor, and then this is another. So then we can use product over sum. So if one resistor is 2 plus 4, then the other one is 9. So this is the product, and then the 2 plus 4 is one resistor plus the other one, which is 9. So this is the product over sum. Remember, this can only ever be used for 2 resistors. So this is one and this is another one. So when we work this out, this turns out to be 3.6 ohms. Part B, the battery current. So we know that across this resulting resistance, we have a 3 volts potential difference appearing. So we can use V equals to IR. So 3 equals to I times 3.6. So the battery current then turns out to be 0.8333. So just to 2SF, this will be 0.83 amperes. Part C, the power supplied to each resistor. So for the power supplied, again you have a lot of the formula. So we have P equals VI, we have I square R, we have V square upon R. So in situations like these, you have to be very sensible about what would save you the greatest amount of time and what would be the easiest to work with. So power supplied to each resistor, remember that we cannot use this current with any of the resistances because this is the total current. You know that in the parallel branch in both of these, the resistance, the current would branch out, right? But what you do know is the voltage across all of this and all of this. So for example, if I start out with the 9 ohm resistor, so if I'm finding the power supplied by the 9 ohm, supplied to the 9 ohm, so I can just use V square upon R because I know that the 3 volt appears across it and its resistance is 9. So 3 square upon 9. So this is 9 upon 9. This is 1 watts. But if you think about it, then for the other two resistors, the one which have 2 ohm and 4 ohm resistances, I would need the current in some sense, or you can also use potential division. So if 3 volts appears across both of these, then we know that, for example, if we calculate the voltage across the 2 ohm resistor, so that would be the 2 upon the 2 plus the 4, right? So the resistance of 1 divided by the total resistance of both multiplied by the voltage appearing in net across both of these. So 3 appears across these ends. So that would give me the voltage appearing across the 2 ohm resistor. So that would be 1 volt. And then I can see that the remaining 2 volts, because the total is 3, must be appearing across the 4 ohm resistor. Right, so basically 3 minus 1 gives me 2. And now I can use P equals V square upon R for these as well. So for the 2 ohm resistor, the voltage is 1. So 1 square upon 2, right? So the voltage is 1, resistance is 2. So this turns out to be half watts, so 0.5 watts. And then for the 4 ohm resistor, it would be V square upon R again, right? So voltage is 2 and the resistance is, so actually the resistance is 4 this time. So this would be 1 watt as well. So this and this are the answers for our powers supplied to each resistor. Part D says the power supplied by the battery. Again, we know the current flowing in this entire circuit is the battery current. We know the voltage across the battery. So we can use P equals VI to find the power supplied by the battery. So that's going to be P equals VI. So V is 3. And if you use the exact value of the current, if you did this in your calculator, you might have noticed this is 5 upon 6. So if you just go ahead and use your calculator value, this will also turn out to be an exact value. And this is 2.5 watts. Right, so this 1 and 1 and 0.5 are adding up to 2.5 watts. So in cases like these, you can always double check these values to make sure that your answers are correct. So because this video is about KCL, what you could have also done is at this part, using the power supplied to each resistor, you can have also done this, that the voltage across this is 3 and 3, and then you calculate this current, and then since the total flowing into this junction is 0.83, then 0.83 minus the current through this would give you the current through this, and then you could have used P equals I square R as well. So it's a matter of preference more than any rule, right? So it's totally up to you whatever you want to do. Let's have a look at this one. So what we have to do, and again the question part for this is missing. So if we calculate the total resistance, let's say these are the points A and B. So if we need to calculate the total resistance between these points, we can see that the current flowing would pass through this and then it would branch out into this, right? So it would branch out between the 4 and the 2 ohm resistors. So we can see that these two are in parallel, and then the parallel combination of these would be in series with this. So if we need to find the total resistance in what we'll now call part A, that would be the 3 plus the parallel combination of 4 and 2. So again, because this is 2 resistors, we can use product over sum. So 3 plus 8 upon 6. So 3 plus 4 upon 3 basically, and this would be 4.33 or 4.3 ohms. Now the second part, part B, is what I am more interested in. So we need to now find the effective resistance between the points A and B. So remember that when I was talking about this in an earlier example, I said that it needs to be very clear that when we calculate the resistance, it's based on the flow of current. So the current is entering in a position like this, right? We know that it would branch out into both of these, right? So from this part it would flow like this. So the same current flows through the 20 and the 10, and from this part the same current flows through the 100 and the 50, and this is where it branches out. So I can say that for this part, so definitely because this is branching out, this part, all of this must be in parallel with all of this part. But within this part itself, the 20 and 100, the 20 and 10 are in series because the same current flows through them. And similarly, the 150 are in series, right? And this is where the current flows out of. So if we need to find the total resistance in this part, that would be the 20 and the 10, which can be represented as one resistor, in parallel with the 150. So again, effectively these are two resistances, so we can again use product over sum. So the 20 plus 10 multiplied by the other resistor, which is 100 plus 50, and then product is done, so upon the sum, so 20 plus 10 plus the other resistor, which is 100 plus 50. So just go ahead and work this out. This should turn out to be 25 ohms. Let's have a look at the last question. Let's have a look at the question itself. In the circuit of figure 10.32, the currents I1 and I2 are equal. So this is I1 in one branch, I2 is the current in the other branch. Both of these are equal. Calculate the resistance R of the unknown resistor. Now it's pretty obvious that if you know the voltage across either of these, you can also calculate the current. But for the first part, there is a smarter way to work through this, which is this, that if the currents I1 and I2 are equal, then this means that the resistances of each of these branches must also be equal, right? That's the only way that the current branches out equally, because current branches out in a inverse proportion to the resistance, right? This is what happens in parallel circuits. So whatever is this must also be this, so the resistances must be the same. So then I can say for the lower branch, I can say that the R, which is the unknown resistor, plus 5 must be 10 ohms. So then R would be 10 minus 5, which is also 5 ohms. Part B, the total current I3. And in this part, again, you cannot skip the calculations. So the total current I3. So what we can do is that we can find I1, because we know the voltage across this is 15. So V equals to IR, 15 equals to I. So this is basically I1 we are finding times 10. So I1 would be 15 upon 10, which is going to be 1.5 amperes, right? So we know that by the statement given initially, that means that I2, which is also I1, would be 1.5 amperes. And if we apply KCL, Kirchhoff's current law here, the current flowing in is I3, current flowing out is I1 and I2. So I3 would be I1 plus I2. And you can also think of it as the, so twice of either I1 or I2. Anyway, the math works out in a way that it gives you I3 as 3.0 or 3 amperes.